Yeah, thank you very much. So, as introduction was said, I was supposed to be here with Bartek, but unfortunately he's not with us. So I will cover, at least try to cover his part as well. And at the beginning, I would like also to thank you, Umit, who is our data scientist. We work together in the Watson Machine Learning team in Krakow. Currently, he has moved to the elite team, data science elite team, and we work together on some slides here. So I hope that you will find them quite useful. Okay, so I will start with the problem introduction. So as I mentioned, we work on Watson Machine Learning service. So I will combine some knowledge that I have from machine learning field as well as from software engineering, like processing, streaming data, and that's mainly the subject of this talk for the reason of this section, so reactive programming. So then I will cover the Spark structured streaming, which is still quite a new feature of Spark, developed in early Spark 2.0, and now I think it's starting to get to be quite mature. Not, let's say, fully complete, but good enough to start playing with it. And then I will present some use cases from our experience when working with Akka streams. I'm really glad that the previous presentation was about Alpaca, because we are using quite a few connectors from there. So for those of you who listened to the previous presentation, very good one. It probably would be a good continuation. Okay, so what I'm going to talk about, mainly about the cloud, which is distributed around the world, nothing new. And the production system, we can imagine that in particular regions we have a few availability zones. In each availability zone we have hundreds of or even thousands of containers that are serving the particular functionality. In our world, that would be the functionality related to scoring of machine learning models. So in that containers, we are going to serve machine learning models and the scoring functionality. It would be very easy if we could deploy particular model on the single container, get the isolation level proper in such way, and we are mainly done. But because of the cost efficiency, especially for very small models, we need to deal with multiple models, or sometimes dozens of models on the single container. So the whole problem with interference between tenants starts to occur. Okay, so one word about our service. I mentioned that we are serving scoring functionality with some additions and as well as training for machine learning. So for example, for Spark ML frameworks, scikit-learn and others, as well as for deep learning, so TensorFlow, Keras, Kafka. Mainly all mainstream frameworks are supported, so you can deploy your model and you are done. You can get your REST API endpoint, or you can get the real-time stream for your model. So, as I mentioned, at first we need to deal with multi-tenancy, at second with variance of frameworks, and finally with the many purposes of the data analysis that came from the computation cluster. So I would not focus on the functionality of our service. I would focus on the stream processing of usage data. So mainly the side effect of the processing in the cluster. So any kind of metrics that allow us to measure many things, including billing stuff, instrumentation, monitoring, and as well as some kind of analysis, also offline analysis. Okay, so what are the challenges? The first one, and I think the most important, I already mentioned, so the fact that one tenant can influence the another. So that's quite a problematic use case. We are charging for computation time, so that's quite risky, because if you would provide poor infrastructure, the clients needs to pay more. That's good for you, but unfortunately not for the clients. And there is a last very small and very simple thing, but it will allow me to present you the way how to deal with real-time processing. So free plan limits, what does it mean? These are mainly the limitations on the free users. For example, you can make only 5,000 predictions a month, or you can train for 5 hours a month, something like that. Okay, so I will go through some steps in this presentation. I will start with aggregation using Spark, as well as machine learning. Then I will go describe quickly the real-time monitoring with some eventing that would use Akka, and finally the interaction with some external sources that also would be done with Akka. I like this diagram. It's not so complicated, maybe even it's very simple, but it will allow me to guide you from the whole process or data flow that we can talk about, or imagine as a simplified example what can happen in processing streaming data. So we have on the left 3 examples of free sources, streaming sources. For simplicity, all of them are Kafka topics. So we have some usage data, which mainly contain information how the user was, how user used our resources in the cluster. We have some monitoring data, and finally some events that came from API. We would like to combine all this data together and aggregate it and prepare some features that will allow us to build the machine learning pipeline and train the machine learning model. Before we would be able to train the machine learning model, we need to have training data, and I will cover in this talk the supervised learning. So we need also to label this data. So we need to at first store this data somewhere. It can be an object storage. Label this data and train the model. Finally, we can deploy this model and enrich our metrics with, in this case, information how probable it is that some anomaly occurred in the particular, let's say, interval for which we are looking at. Okay, so let's start with Spark structured streaming. Who played with Spark streaming at all? One person. With structured streaming? One. Okay. Who played with Spark? Okay, not good, not bad. And Kafka? Yeah, I suppose. Okay, so from Kafka, or the knowledge about Kafka, we only need to know that Kafka has topics. Each topic is split into partitions, and consumers can read from particular partitions and are supposed to maintain the offset where they stopped reading. This offset can be kept in the zookeeper, but it's not the case for Spark, or at least for the next version of streaming, which is the structured streaming. So topics, partitions, offsets maintained by consumers. This is, let's say, a bit more complicated diagram. So I should look like now as a meaningful person. Okay, so how the integration between Kafka and Spark is realized. I was really surprised that it's so easy. So probably I would be able to explain it to you. So as I said at first, Spark needs to maintain the offsets when he stopped reading the data. And that's not done on the zookeeper because of the bottleneck which was created by the zookeeper. So now in the new version of Spark streaming, offsets are stored in something named checkpoints or checkpoints location, and these checkpoints are usually stored on HDFS. So pretty simple. That's the first part. What is the second? We would like to have some consistency or some guarantee of delivering the messages. Let's say the basic one is at least once delivery. So what Spark needs from the source to achieve at least once delivery? A very simple thing. Ability to replay the messages. When the Spark node goes down, when any kind of failure occurs, it will simply replay data from the place which was stored in the checkpoints. That's it. It can produce duplicates. That's the risk. So what we need to support on the downstream system to achieve exactly once delivery. So either this sync needs to support or somehow deal with duplicates, or we need to simply deduplicate data before we write to this destination. From the Kafka perspective, if we will talk about the Kafka as an output, then we need to remember that Kafka itself, up till version 0.11, doesn't support exactly once delivery. So that's quite tricky, because even if we will deduplicate data in Spark, then the message can be duplicated on the Kafka. But that's, let's say, a detail. It's not so difficult to deal with duplicates, and usually systems are prepared for it. And one more thing about Kafka, it's a partitioning which is quite crucial to support parallelism on the expected level. So usually quite important question is how many partitions I need to create. And to be honest, it's not an easy question, because if I would create 2 less partitions, I would not be prepared for the scaling in future, and we mainly experience how difficult it is to repartition the Kafka topic in the production system. So there is no automated way, everything is manual. So you need to think about it upfront before you will design your system. And of course, having too many partitions is an overhead you would like to avoid. Okay, so that's all about Kafka, Spark, and integration between Kafka and Spark. Now let's move to some fancy stuff I like very much from the structured streaming. So for those of you who knows how the previous version of streaming in Spark worked, it mainly worked with the microbatches and RDDs, which were represented as microbatches, and you had to deal with the portions of data on your own. Currently, in the structured streaming, the stream is represented as an unbound table. So you can treat it as a data frame or even data set, in exactly the same way how batch processing is, or batch data is processed on Spark. There is one really nice guarantee served by Spark. This is named prefix integrity. So that means whatever data at a particular time you will get from the stream and process with structured streaming, and in parallel you will process this data with batch processing, you will get exactly the same results. It's really awesome. If you would think how it influences the data preparation work, usually when you build your machine learning models, you work on some static data, offline data, not on the real-time stream. So you build your data preparation pipeline with Spark map reduce operations, and then you have to somehow repeat the same for your streaming data. And with such guarantee, you can simply copy-paste the code mostly. I will show you some examples, but it's not so straightforward. But at least such guarantee is really helpful to build the data preparation flow. If you deal with transactional sources, Spark would also support transactions on the level of on the storage side. So you can simply update your data in transactional store with the guarantee of serving transactions. The data frame and dataset API works pretty much the same as for batch processing, and that's a huge difference in comparison to the previous streaming version, which used a totally different API. And the last nice feature is the event time, which simply allows you to think about your streaming data as a time series data. And so that's given for you without an effort. Okay, so let's go to some nice parts, so code snippets and examples. This is a very basic example which tries to show how similar are versions for streaming and batch. So on the left you have read stream, on the right you have read, and that's the only difference. Here you have write stream, there write to Parquet, everything else is the same. The only difference is here, which is start. So this would block on the driver and until the write operation would finish. This would not block because we are starting the stream. We are getting as a result here the query. That's the only difference. Maybe I will mention here that you can run in the particular Spark application many streams, so that there's no limitation that you have to control the stream. Probably this is not so interesting, or I will skip it a little, but this diagram or this picture is quite interesting. It simply shows how the streaming data is aggregated in time and what's outputted, what is the result of processing data in particular moments of time. So I think this mode, this output mode is the most important, and it simply tells that Spark would update only the data that has changed since the last moment in time. Others are complete. For example, is sometimes used for memory stores. Append, it's not so often used. Okay, how to listen to Kafka messages. Beside this stuff related to authentication and things like that, you have only to specify the topic or topics, the list of brokers, how you want to, from where you want to start. So from the beginning or from the last message, and that's all. So you have your stream, and it's a data frame. So if you know the Spark API, you already have the access to data frame. Structured streamings, as named, deals with structures. So you can deserialize your data, and here's an example for JSON. It can be Avro or whatever. But the key point is here, the data structure. For batch, usually Spark tries to infer the data structure from database or from file. For streaming, there is no such a possibility, so you need to provide the structure on your own. So that's the first thing. As a result here, I'm getting the data frame with rows well defined. And what more, I can define my case class, and I end up with the dataset, which is fully typed dataset. And I now can play with my dataset in exactly the same way as I would do this with batch processing. For me, really, really powerful. Okay, so once we have data from Kafka, we would like to make some operations of this data. So let's start with joins. That's all. Join three streams together, you're done. Even for streaming sources, you can join some data from databases or from files, but I think the most tricky part is joining streams together. If you will see here, there is a join tab which is left outer join, and that's a new feature of Spark 2.3 which was released a month ago. And it's not so easy because it's easy to say that you don't have particular data to join with another data if you deal with the offline database or offline table. But what when you deal with stream, which is continuous, and you can have some data which hasn't arrived yet? And for that purposes, there is a parameter like watermark, which will allow you to decide when to consider that the particular data needs to be marked as null, so doesn't exist for your join. Yeah, that was quite nice to when they introduced that last time. Okay, so I have my data, I have the join result. I would like to persist it in another Kafka topic. As simple as you can see, I'm writing the stream here. These are the parameters quite similar to the reading the stream. You have your checkpoint location. So the first time we are pointing where offset are stored and starting the query. That's all. What's nice, from the query you can monitor it easily. So you have some properties like last progress, and you can get from it, for example, offsets of your particular partitions, or the processing rate, or the watermark, or the timestamp. So all such things are easy to retrieve from the metadata of the stream of the particular query. And even more, you can register your listener, so you can be reactive and you can react on, for example, query termination and restart it. Okay, so we have stored data on the another topic which aggregated the data. Let's do some more fancy stuff like grouping by windowing function, aggregating the data, counting averages, minimum, maximals, and things like that. Still with watermarks, mainly for late data. So it's a problem how long I should wait for the data, or how long I would include the data in the aggregation. So in this example, I will wait a minute until I will finalize the aggregation and return the result. Okay, so mainly that's all for at this moment for data preparation. There would be one additional slide, but before that, let's go very quickly to some data samples. These are only the samples, quite simplified, but should show you how you can think about the problem. So we are talking about the computation time, which is in green here. Here we have a red axis which points the maximum values in particular time and the minimum values. So you have some average computation time on particular pod or for particular model. So this is the first data we analyze. The second is the state of our container or the group of containers. So the memory usage, CPU usage, file system usage. Simple. And finally, an example of some events. Here in particular, there are the events related to the number of deployments in particular seconds, or in particular, I don't remember, probably 10 of seconds. Such events tend to be quite important for our machine learning models because they influence it a lot, the computation time in some time. Okay, so how we can, let's say, think about our data from the machine learning perspective and what we would like to do with this data to be able to build some model. So we are going to calculate the moving average in the window, I think 15 minutes or something like that. So we are calculating the average in the 15 minutes average in the past and comparing it mainly, so calculating the distance to the current value. So this distance is in the blue and the moving average is in the magenta. Okay, so how we can calculate moving average. In batch processing, it would be as beauty as this piece of code. So clean, so nice, really powerful. Unfortunately, this is one of the parts which is not supported or structured streaming. We found a way to work around it, but it doesn't look so nicely and has some side effects. But still we can work out it. Okay, so we have our data prepared. Let's build the machine learning model. This is a sample of some, let's say, time series data for computation time, or even the average change of the computation time in comparison to the moving average, and some points that shows where are anomalies. So labeled data mainly. We are writing this data to HDFS or S3 or whatever to train our models. Here, for those of you who knows machine learning, is a very simple example of a machine learning pipeline. It uses some features from our data set, so mainly all the features that we talked about. It also normalizes the features and use the random forest classifier for labeled data. In such a way we are able to finalize our machine learning pipeline and train the model on the labeled data. This labeled data could come from the object store on which we stored the data before. Then we can save this model, of course, in the Watson machine learning service or anywhere else, and use this model for making predictions. And I don't know if you see it, but in Spark, all the scoring is done with this single line of code for streaming data. That's quite new, because for previous streaming it wasn't so easy. For batch it is, but for now you can play with your streaming data in exactly the same manner as with batch data. So transformation, machine learning transformations are supported in exactly the same way. Okay, and as a result, we have our data on another Kafka topic with predictions. What next, and why I would even think about something like Watson machine learning service if the code for scoring is so simple? Because of maintaining the model. I would not go into details. Łukasz, my colleague from our team, is going to have a separate presentation on continuous learning on the data sphere in, I think, an hour or an hour and a half. So he will definitely cover this part for you if you would like to listen. But continuous learning is mainly about gathering the feedback data and retraining the model once the feedback data brings some novelty to your model. Where to get the feedback data? Mainly from, in our case, from experiments for PagerDuty alerts. So DevOps operators can simply label this data. From offline analysis, at worst, from customer complaints. Yeah. Okay, so that's all for Spark. Let's move to Akka streams. We use them in, as I said, for two cases. One, the real-time events. Why? Because at least from our observations, the latency on Spark is quite big. They are claiming that it's around few hundreds milliseconds. We have experienced rather 1 or 2 seconds at best. So it's quite big latency if you really need to react quickly on some change in the system. So there's where we find Akka Kafka connector quite useful. And the second part is on outputs, so integration with any outputs. We are on the way to, or at least on the way to start our contribution to Alpaca. We have prepared one very simple tool for, let's say, addition to Akka streams, I don't know if that would be the good candidate, but for sure the second topic we would like to publish, so that would be the Cloud connector. But what we found missing in Akka Kafka is mainly the actor that will monitor the state of the consumer. It's quite often that your stream would finalize because of some failure, and there is no simple way to react on such failure. So we mainly implemented some simple actor that you can plug into your Akka flow, and it will allow you to restart the consumer once it's down, and on the other hand, it would allow you to get some statistics of processing, and that's, I think, very interesting. We had a small talk previously about having an insight, for example, how many messages were processed on or more particular topics, or how many messages are waiting. So there is no good monitoring tool for Akka streams up till now. We are waiting for it, so we are trying to somehow work out with some simple tools that gather statistics and serve them to be able to publish them. So this is the example of the statistics you can get. They are quite similar to ones from Spark streaming, I guess. I found it lately that they are quite similar. Okay, and the last topic is a Cloud connector. And that's the work that Bartek worked for last at least year or even more. And it's really powerful. Beside the fact that there was no connector to Cloud in Scala, so we started mainly with the implementation of the Cloud connector. Then we realized that we not only need the Cloud connector, but we really need to have a Akka Streams connector. And here is an example. Oops, sorry. Not this button. So this is the example of this Cloud connection sync. So you can simply generate some documents and store in the sync. The same for query. Bartek invented SauDSL for query on Cloud, and you can treat this query as a source for your data. And finally, I think quite nice feature, you can also monitor the changes on documents. So any kind of modification of the Cloud document or addition, removal can trigger the event, and you can observe this event also in the form of the Akka source. So that's hopefully would allow to. It was very useful for us. So hopefully we would get approvals to make it an open source project for you. Yeah, and very simple example of some aggregation used from the changes stream through the Akka streams. Akka streams was covered so many times during this conference that I'm glad that I don't have to go into details. Okay, so let's summarize. We have talked about quite largely about the Spark streaming and a bit about Akka streams. This is the main difference, and this is the main difference. So if you deal with a lot of data, then Spark streaming would be perfect. If you really need to have a very low latency, probably Akka streams would be better. But I read that Spark is working on the continuous processing, which would support or which would provide the latency on the level of single microseconds. Quite interesting. I'm really happy to see it in future. I haven't talked at all about Flink or Kafka streams. I think Kafka streams are not really interesting. Flink seems to be quite an alternative. Up to this point, I was really surprised when I found these benchmarks. It was on the Databricks sites. I thought that Flink is faster than Spark, at least it was in the past. Currently, the current version of the Spark is faster than Flink. For me, it was quite a surprise. So to be honest, in our use cases, I don't see a reason why we should use Flink instead of Spark streaming, the new Spark streaming, not the previous one. Okay, thank you very much. That's all. Yeah, for sure I will be glad to answer any questions if there are any. Yes, alpaca connector. So Akaka. Yes, yes. Yep. Yep. Yes, mainly you define the timestamp on your own. So this is the timestamps which is in your message, and you can build your data frame on this using this timestamp. So you can simply create a window function using that timestamp you provided. Yes, yes. So Spark mainly deals with ordering of data. Any more questions? So thank you very much.